This is section 13.5, part A, and also part 2. We're going to look at some examples now using cylindrical coordinates, beginning with just converting back and forth between a rectangular coordinate and a cylindrical coordinate. So in rectangular coordinates, we have the point 1, negative 1, 5, and we certainly all know how to locate that. Just out 1 on the x-axis, over negative 1 on the y, and then up 5 on the z. We'd like to now know how to describe that with cylindrical coordinates. So I'm going to use my conversions. We know, first of all, that x squared plus y squared equals r squared. So plugging in the x and y values from our point, 1 plus 1 is going to give me 2 for r squared. And r would be the square root of 2. I also know that the tangent of theta is equal to y over x. So in this case, that would be negative 1 divided by 1, or negative 1. And here I do need to use just a little bit of information about the location of the point in order to determine the exact value of theta. Tangent of theta is negative 1 in both the second quadrant and the fourth quadrant. I need to know which one I'm at. So since my x is 1 and my y is negative 1, in the xy plane, I would be down here in the fourth quadrant, meaning my theta is going to be a fourth quadrant angle. And both looking at that and also with a little bit of help perhaps from your unit circle, we can identify our theta value as 7 pi over 4. Finally, the z value doesn't change. Z is still z, so z is still equal to 5. And that means my point is going to be the square root of 2, 7 pi over 4, 5. A couple of quick things that I did automatically here, but maybe I haven't talked about so much. First of all, I did take just the positive square root. I think we might have talked about that just a little bit. We're always going to assume that r is positive when we write our cylindrical coordinates, just to eliminate any confusion. And similarly with the theta, I could have used a negative angle here for theta, but I chose to go with the positive 7 pi over 4. We'll restrict ourselves to thetas between 0 and 2 pi. Again, just to eliminate some of the confusion that exists when we allow for other values of theta. Negative values, going around the circle more than once, things like that. We're doing everything we can to make our coordinates as unique as possible. Also notice the order I wrote them in. It's always r, theta, z. All right, in part B, we're going to go the other way. This time I've given us cylindrical coordinates, and we want rectangular coordinates. So I need x, y, and z. I know that x is r cosine theta. That would be 2 cosine pi thirds here. Cosine of pi thirds is a half. So x is 1. Y is r sine theta. And that would be 2 sine pi thirds. Sine of pi thirds is the square root of 3 over 2. So that's going to give me the square root of 3. And z is still z. So z equals 5. And here are my rectangular coordinates. 1, square root 3, 5. You'll notice that I did make use of all 4 of my conversion equations. Those are our polar rectangular conversion equations, and they also serve us well for cylindrical coordinates. was really all just to kind of get us a little bit familiar with what cylindrical coordinates are. What we really want to do, though, is talk about how we set up integrals with cylindrical coordinates. So, first of all, if I want to integrate a function in cylindrical coordinates, r, theta, and z, over a three-dimensional object d, my differential here is dv, then I'm going to integrate over that three-dimensional object my function. And instead of dz being dx, dy, dz in some order, like we've been doing, I'm now going to use the polar form instead of the dx and the dy. So I'll have a r dr d theta, like we usually do in polar coordinates. And then I need that third variable, that dz, as well. I did specifically write it in this order. This is typically the way that we set them up, although like other integrals, if I want to change the order of integration, and it's possible, I will sometimes do that. So in this case, our big takeaway is our dv is now r dz dr d theta. So let's use that to set up our example 2, a triple integral that finds the volume in the first octant of the solid bounded by z equals x squared plus y squared and z equals 9. First of all, I'm thinking cylindrical coordinates would be really nice here because that x squared plus y squared would just be an r squared. Which is a really nice simple way of writing it. So we'll probably use cylindrical coordinates. Let's think about what this shape looks like. I'm going to try and sketch, and then I'll also show you a maple graph. This is that paraboloid, z equals x squared plus y squared, or z equals r squared. Like so, centered at 0, 0, and opening around the z-axis. And z equals 9 is just the horizontal plane that's going to kind of create a top on this. Technically it cuts through the whole paraboloid, but I'm going to assume I stopped just in time. So z equals 9 is that piece of the horizontal plane that tops off the paraboloid. This again is z equals r squared. If I switch over to my maple picture for a moment, you'll notice here with my implicit plot 3D, I did plot my paraboloid and then my plane. And this shows you a little bit more of an overall picture. The paraboloid here, I've extended it above z equals 9 as well. And then you can see that plane z equals 9 slicing through horizontally. If I rotate this just a little bit, you can see that circular intersection inside the paraboloid. All right, speaking of the circular intersection, that circular intersection projected down into the xy plane forms the region R. So that's my R, except down here in the xy plane. If I set the z's equal to one another to find the intersection, that's r squared equals 9. That gives me r equals 3, or a circle of radius 3. And I do want to make one slight course correction here. I really only wanted the volume in the first octant. So instead of using that entire circle, I'm going to choose my r to be just a quarter of the circle, the first quadrant, which three-dimensionally will eventually limit me to the first octant. All right, so let's go ahead and set up our volume integral. When we do volume with a triple integral, we'll always integrate the function 1. And then I'm going to put in my dv, which is r dz dr d theta. And for the dz limits, I go from bottom to top. The lower limit would be the r squared, and the upper limit would be the 9. For r and theta, I'm going to look at my r picture. If I imagine my radial spoke, I'm already in my region at an r of 0, and I exit the region at an r of 3. Finally, I start at theta equals 0, and I sweep this out to go to theta equals pi halves. Get rid of my email reminder here so I don't keep making you listen to that. There we go. All right, so that's our setup for our integral, and we are ready to solve. So I'm going to integrate, before I do, let's use our trick again. Notice here that indeed there is no theta anywhere in this integral except the d theta. So I can use our old trick and say, let's just get rid of the theta integral. We know it will automatically give us a multiplier of pi halves. I then have the second integral, which is 0 to 3. In this first one, I'm integrating r dz, which will just be rz, evaluated from z equals r squared to z equals 9. The r out here waiting its turn. All right, plugging in, z is 9 is going to give me a 9r, minus when z is r squared, r times r squared will give me r cubed. And my integral is set up now to the point where I can finish it on the calculator. Let's see here. I know I did this one. There it is. When I did that integral, I got 81 fourths. So I really have pi over 2 times 81 fourths, or 81 pi over 8. All right, let's set up one more triple integral like that before we pause and move on to another video. Example 2 is quite similar. We want the mass of the solid above the xy plane. Below this cone, notice this cone has been shifted up 4 and turned upside down with that negative. And also inside this cylinder, x squared plus y squared equals 4, given the density function 5 minus z. So if we think about this for a moment, this cylinder is a circular cylinder. It's a circle of radius 2 in the xy plane, parallel to the z-axis. So if I start thinking about my sketch, again in the xy plane, here's the circle of radius 2 going up parallel to the z-axis. Now the cone is going to have its vertex at a height of z equals 4. And then the cone is flipped upside down. So it's going to come down, and technically the cone goes down forever, but I'm only going to draw it as far as it would intersect the cylinder. Because if I went beyond that out here, I would no longer be inside the cylinder. All right. So let's see what we've got. We have got the solid above the xy plane. So the base here, which will eventually also be my r, is just z equals 0 in the xy plane. The cone itself is the top. And I'm going to notice that with all the x squareds and y squareds, and the fact that my region here is going to be a circle, cylindrical coordinates seems like a really good idea. So I'm going to change that to 4 minus the square root of x squared plus y squared is r squared, or just 4 minus r. And then finally, the cylinder, the sidewall here, is r squared equals 4, or just r equals 2. Before I set up my integral, let me also just sketch the region R. It's this circle in the xy plane. We already know the equation of that circle is r equals 2. And it didn't say anything about limiting to a certain octant or anything, so in this case we'll use the entire circle as R, the region. All right, my picture may or may not be wonderful for you, and in case you're not seeing it as well as you would like to, let me just pop over to Maple here again for a moment. And here is a little bit of help for graphing this in Maple. I've done something a little bit different here, and I would encourage you, if you do have Maple at home, to study the command a little bit more closely. But I'm going to show you a couple quick new things in case you're trying to use this. I graphed the cone, so the whole cone down to the xy plane, z equals 4 minus the square root of x squared plus y squared. And I've done a couple things. I've assigned it a name. I've called it P1 for plot 1. And then I used the colon equal to assign P1 to represent this plot. I've also done two other things at the end which we've not seen before. I've assigned a transparency factor of 0.2 so that later on I can see through the cone. And then the style I've set to surface contour, which draws just the contour lines rather than so many lines around the cone. I've also assigned P2 colon equals, and here's the cylinder, x squared plus y squared equals 4. I have not made that transparent, I've just left it the way it usually is. To see them on the same graph, I've now said display P1 and P2, and so here they are together. And because of the transparency of the cone, you can see the cylinder in here inside it. So here's that cylinder that's on the bottom, and then here's the cone that forms the top of our shape. All right, going back to the actual calculation then, I need the mass, and to get the mass, I know I need the triple integral of the density function, 5 minus z. I'm going to be doing this in cylindrical coordinates, so the dv is r, dz, dr, d theta. My z limits of integration go from the bottom, which is in the xy plane, z equals 0, to the top, which is the cone, 4 minus r. The cylinder itself doesn't get involved until I get to the r and theta, because the cylinder is what defined that region r for me. If I think of my radial spoke, I do start at an r value of 0, and I leave the region at an r value of 2. And since I want to go all the way around the circle this time, my thetas would go from 0 to 2 pi. Let's go ahead and calculate the value of this integral. I am going to use my trick for theta. There are no thetas anywhere in this integral except for the d theta. So I know that I'm going to have a 2 pi as a multiplier. I would like to integrate 5 minus z times r with respect to z. So r is a constant multiplier. I'm just going to keep it there. And then integrating the 5 minus z, I'll get 5z minus 1/2 z squared. And that goes from z equals 0 to z equals 4 minus r, with the dr integral still waiting. So let's see, I have r times 5 times 4 minus r, subtract 1/2 times 4 minus r squared, minus, when I plug in z equals 0, everything just becomes 0. And I need to integrate that dr. This is where I'm going to do my calculator technology integral. And let's see, when I did that, excuse me just a second, looks like I didn't. I'm going to pause and type that in. All right, when I typed that one in, I got 58/3. So what's that going to give me? 1/16/3 when I multiply by the 2 times pi. All right, we will stop there for now and pick up a couple more examples in our last video for this section.